So again, to get started with polynomials here and their division, let's just recall how to divide a number. Okay, so this is going back a few years here, but to do long division, we'll put 11, then we'll put our division symbol, and then we get 6372 will be underneath the division symbol there. It's probably a great name for that. I'm not really sure what it is. 11 is called the divisor, and the thing being divided is called the dividend. Just kind of some words that we'll use here. So hopefully you remember that to do this, the first thing we'll do is we'll look at the number 11, which is the divisor, and we'll see if it goes into 6. It doesn't, right? So you start from the bigger end of the dividend. So does 11 go into 6? No, it doesn't. So we look at the next digits here. So we have 63. So does 11 go into 63? Well, it does, but not evenly, right? But it goes in 5 times, right? 11 times 5 is 55. So I'm going to go ahead and put a 5 up here on top. Some people put it out over the 6. I kind of put it over the 3 just because we're going into 63. So we'll do 5 times 11. That'll give us 55. And then we remember division is just repeated subtraction, correct? So what we're going to do here is we're going to take that 63 and we're going to subtract 55 from it. So upon doing that, we get 8, and then you'll bring down one more digit. So I'm going to bring down the 7. So hopefully that seems familiar, right? Going a little back a few years. So here, how many times does 11 go into 87? Well, it's not 8 times because that would be 88, so it must be 7 times. So we'll go ahead and put a 7 up here, and then 7 times 11 is 77. Subtract again, and we get 10. We'll bring down one more digit, right? So we're just pulling down additional digits. And then how many times does 11 go into 110? Or I'm sorry, 102? Well, I do know that 99 goes into that, right? So 99 is 9 times 11. So we'll put a 9 up top. 9 times 11 is 99. Subtract that, and that gives us 3. Now, here's where probably originally when you learned to divide in grade school, you probably stopped here and just called this the remainder, right? And that's what we want to do now. That's going to be most applicable to what we're doing with polynomials. I know that right after this in grade school that you learn about decimals, so you start pulling down more zeros and you have a decimal place. We don't really, I mean, that's still valid, it's still a thing, but it doesn't really help us here. So we would be done here. So we would say that 11 goes into 6,372 579 times with the remainder of 3. Right? So you might have said R3 to remind you remainder 3. We know they're there because we ran out of stuff, right? We just know the remainder has to be smaller than the divisor. So let's just kind of use this one to look at the names of our pieces. So with this, 6,372 is called the dividend. That's the thing being divided. And then 11 is called the divisor. The answer is called the quotient. And then down here, we have the remainder. Now, when we're looking at polynomial division, we tend to give those polynomial names. We tend to call the dividend, the thing being divided, p of x. And then we call the divisor d of x. Right, just d is the name of the function, d of x. Call the quotient q of x, and the remainder r of x. Because what we'll find here is that when there's a couple ways to kind of write out your answers to division questions. And we're going to use this with polynomials too, is if you do the quotient, or I'm sorry, the dividend p of x, right? If we multiply if we divide that by the divisor, right? So the dividend divided by the divisor is the quotient plus the remainder over the divisor, is one way that could be written out. So in terms of our numbers, that would mean 6,372 divided by 11 is 579 plus 3 11ths. Would be one way that you could write this answer out. Okay. So again, dividend, oh, sorry, I forgot to put a parenthesis there. Divisor equals quotient plus the remainder over the divisor. So that's one way that could look. And that's fine, that was a great way. Another way though, kind of gets rid of the fractions, is if you look at this expression, you notice that both of these are being divided by d of x. Right? If we multiply this thing by d of x, these two will cancel, it'll put a d of x up here. So the other way to look at it would be p of x equals q of x times d of x plus r of x. So again, I just multiplied by d of x to each place, or each term. So then here we would get 6,372, 579 times 11 plus 3. So if you check, both of these will be true, right? Both of these statements. That's just how we can talk about what our division answer would be. These have different names. A lot of times the problem will ask you to express the answer in one of these ways. Like on the Delta math assignments, I think it uses this one some. I think our textbook uses them both a little bit, but maybe this one a little bit more. If I'm asking for an answer on a quiz or something, I would say, write it using this rule or this rule to write your answer out. Does it make sense how we can express the answers here? Okay, so we'll come back to these ideas right here, and we'll use that when we're actually doing polynomial division too. Okay, so let's go ahead and actually do one with the polynomial function now. Again, these are the two ways we can write them up, right? This is fine. This one tends to be nice. We'll use this a lot for factoring, because if we can get the remainder to be 0, we just have that this big polynomial is the product of two other polynomials. So it just factors it, which is really a handy thing. So our second example here is we want to find the quotient using long division. Now, last year, you probably did synthetic. You should have done synthetic division, which is an extension of long division. You probably skipped long division if you were in a regular or college prep, algebra 2, maybe honors. I'm not sure you might have done long division. But we're still going to do synthetic. We just need to figure out if it doesn't always work. So you need to have long division available. But here we have 5y plus y squared plus 4 divided by 2 plus y. Okay, so here this would be our dividend, our p of x. Right? This would be our divisor, which would be our d of x, or I guess d of y in this case, the variable. But one thing to do here is whenever you get a problem is that this is not in standard form. We need it to be in standard form for this to work. So let's write this as y squared plus 5y plus 4 divided by y plus 2. Also, these parentheses here would be really important, right? Because we're not just dividing 4 by y, but we're dividing that whole first trinomial by that binomial. So to do this, we'll put our y plus 2 on the outside of the division symbol. And then inside will be y squared plus 5y plus 4. Notice here that we go second degree, first degree, constant. Even if you're like, say, missing a y term, I would probably go ahead and put 0y in there. It's really going to help with your alignment, right? Just like if you had the number 103, you put a 0 in there for the tens place. If you have a power of y that is missing, you'd want to go ahead and put a 0y or 0y squared in there. I think we'll get to look at one on example 2, just to be careful about that. So the first thing I want to look at is really how many times does y plus 2, but specifically y, go into y squared. So we're going to try to get rid of the front piece of the polynomial, kind of work our way back. So if I want y to become y squared, what do I have to multiply it by? Y. Yeah, so I'm going to multiply by y. And then now I'll take this y times both of these terms, and those are going to get put underneath here. Just like we did with the numbers, correct? So y times y is y squared. And then plus y times 2 is 2y. Now here's what will be a little tricky, is to remember that we're still doing division, which is repeated subtraction. So in this case, I want to subtract that whole expression that I just got down here. Right? So I did y times y to get y squared, y times 2 to get 2y. Then I'm going to take these two terms and subtract these two terms. So y squared minus y squared is 0, right? They just cancel out. But then we'll have 5y minus 2y, which is 3y. So that'd be 3y. And then I'm going to bring down the next term, so plus 4. So now this is like what's left over, correct? Now I know that I need to keep going because before with our remainder it needed to be a smaller number than the divisor. Right? With these our remainder will be a smaller degree than our divisor. So since the divisor is first degree, we would expect the remainder to be 0 degree, just a constant. We'll see as we move through these. So I want to look at this thing and I want to get rid of 3y. Right? So how do I make y into 3y? Multiply by 3. Right? So I'm going to do plus 3. So 3 times y is 3y. 3 times 2 is 6. But again, we're going to cancel that out. So 3y minus 3y is just 0. And this will be 4 minus 6. So this will be negative 2. Now once we have that, just to kind of go back and look at our pieces here, again, what's underneath here would be p of x. It's called the dividend. This would be the divisor. This would be the quotient, or the answer to the division problem, if you want to think of it that way. And this would be the remainder, r of x. So if we look at our two different models here, we could do, if you use the left-hand one, you'd get y squared plus 5y plus 4 over y plus 2. Right, so dividend, divisor, and then the quotient here will be y plus 3. The remainder will be plus negative 2. So this is our quotient. So y plus 2 goes into this polynomial y plus 3 times with 2 left over, which doesn't help us factor at all because it says plus, and we can't do that. But if you did, sorry, that's going to be negative 2 over y plus 2. I forgot the divisor there. All right, so these should be equal. Now, this would be a real pain if you tried to add this together to actually check it. So this one ends up being a lot simpler to check. So y squared plus 5y plus 4 is y plus 3, which is the quotient, times the divisor, which is y plus 2, minus the remainder. So that's a lot easier way to look at it in terms of checking, is to use this model right here. So right, the original polynomial, or the original numerator, and then this was the divisor, or the quotient times the divisor, and then that's plus the remainder there, is how we could write that. So it'll depend. Sometimes you'll be asked, what's the quotient? So you'd say y plus 3, or what's the remainder? Say negative 2, or maybe put it in one of these two models and you might write it out. Do this. But this is definitely the easiest way to check it. If we notice here, if we go ahead and distribute this, it's y squared plus 5y plus 6, and then minus 2, and then y squared plus 5y plus 4, which is exactly what we started with there. So there's always a pretty quick check in there as well. So for our second example here, we have 13 plus 4m squared divided by negative 1 plus 2m. So again, we're going to put it in standard form, but also here, if you notice, there's no m term. So I would even go further than standard form. I would put 0m in there to be helpful. So we're going to get 4m squared plus 0m plus 13 divided by 2m minus 1. And then once we do that, to do the division, we would put 2m minus 1 on the outside. And then we have 4m squared plus 0m plus 13. So go ahead and try this one, and then we'll take a look at it. Okay, so let's take a look. So we have it set up. Notice we did put our spacer here, right? That's 0m. So first question is, we're going to attack the head of the monster here, right? The biggest degree first. So if I want 2m to become 4m squared, I have to multiply it by 2m. It doesn't really matter where you put it on top. I always like to have all my m's, my first degree stuff in one row, but it's arbitrary when you do it up there. Underneath it matters. So now we're going to take 2m and we're going to multiply it by 2m minus 1 because that's the divisor. So 2m times 2m is 4m squared. And then 2m times negative 1 is negative 2m. Here's the tricky part though. Once you distribute it, you have to subtract the entire thing. So definitely want to put that in a parenthesis and put a negative out in front. So 4m squared minus 4m squared just cancels. I wouldn't even bother putting a 0 there because that was our whole goal. And then 0 minus negative 2m gives us positive 2m. We'll bring down the next term. You bring down usually just one term, but sometimes if you're going to need more, you can bring down more. See that case. So now 2m goes into 2m once. Like I don't even consider the negative 1 and the 13. Whatever happens with those is going to happen. I'm just looking at that biggest degree part of the polynomial that's left, the 2m. So I'm going to say plus 1. So we get 1 times 2m is 2m and then minus 1. But again, we have to subtract, and this is where we're going to be careful. 2m minus 2m just cancels. 13 minus negative 1 is 14. So that's going to be our remainder. So probably the best way to write this would be, well, let's see. If they ask us what was the original? Well, 4m squared plus 13 divided by 2m minus 1 is 2m plus 1, which is the quotient, plus the remainder over the divisor. So again, it might be written like that. That makes sense? That we're just kind of filling in the pieces. Again, this is our remainder. This is our quotient. This is P, and that's D, if that kind of helps you with the location there. Or we could write it as 4m squared plus 13, which is just the dividend, equals the quotient, which is 2m plus 1, times the divisor, plus the remainder. And this one makes it really easy to check your answer, right? You multiply this out, you see that it works over there. Let's see. Yeah, so just, and again, this was our dividend, quotient, divisor. I guess put x's on them. And then plus the remainder. So that's the idea. So hopefully that went okay. So one thing that we can use to make this easier for us, and kind of a great, really important rule, is called the factor theorem. And it says a polynomial function f of x has a factor of x minus k if and only if f of k is equal to 0. So for that particular function, Now, if we think back to how we looked at zeros when we graphed, right? If you had a factor of x plus 2, you knew there was a 0 at negative 2, correct? This is really saying the same thing. If you have a factor of x minus k, you know that there's an x-intercept or a 0 at k, because when you plug it in, you would get 0 for your function. But another way to look at this is, so if you look at this rule, we had f of x equals the quotient times the dividend. The dividend is the quotient times the divisor, and then plus the remainder. But we notice that if r of x equals 0, then the original f of x is just going to be the quotient times the divisor. So actually, we can use division to help us factor things. Right? So what this tells us is, a related one is that whatever, if you put k into here and you get 0, right, it means that x minus k must be a 0 of that function, or must be a factor of that function. So for our third example here, see why we're worried about this stuff here. It says use the factor theorem to show that x minus c is a factor of p of x for the given value of c. So we're saying we're going to show that, for our example, it would be that x minus 2 is a factor of p of x equals x cubed plus 2x squared minus 3x minus 10. Okay, so we're going to show that this is a factor. So there's two ways we could do that. We could do long division and show that the remainder is 0. If the remainder is 0, right, then we have a factor. Right? That would be kind of a harder way to do that. But we could do that since we know how to do long division. And just to kind of show that, well, yeah, it would be a good, we can maybe look at it. But if it is a factor, so if x minus 2 is a factor of p of x, then that means that p of 2 must equal 0. So instead of going to all the trouble of factoring it out and doing the long division, we can just show that when I put 2 in here, I get an answer of 0, correct? Or actually it was an if and only if statement. So if and only if, meaning it's biconditional, meaning that if this top line is true, this second line has to be true. So let's see, what is p of 2? So p of 2 equals 2 cubed plus 2 times 2 squared minus 3 times 2 minus 10. So let's see, that's going to be 8 plus 8 minus 6 minus 10, which is 16 minus 16, which gives us 0. So what that tells us then, is since it is a factor because we had this 0 here, that tells us that p of x, which was x cubed plus 2x squared minus 3x minus 10, is equal to x minus 2 times some quotient, right? Whatever that quotient would be. But what that tells us is that by doing this division, since we saw that when we plugged in 2, that we got an output of 0 from the function. Right? So we see that 2 is a 0 of this function, correct? And that assures us that x minus 2 must be a factor of this function. So that tells you that we could say that this is a factor of p of x because we showed that when you put 2 in here, you get 0. Now, it doesn't quite show us what the quotient would be. Right? To actually find what the quotient would be, we have to go back and do the long division. So just to take a look at that, that would be the following. That would be, let's see, x minus 2, and then x cubed plus 2x squared minus 3x minus 10. So if we go ahead and do this division, we should get a remainder of 0. Right? The remainder, because p of 2 was 0, that means the remainder should be 0 also. So here we get, let's put an x squared, right? Because we need to get an x cubed to go away. So we multiply, we get x cubed minus 2x squared. But be careful, don't forget we have to subtract, right? A lot of times people see the opposites, they get excited. So we're not that good a thing with division. So x cubed minus x cubed cancels. 2x squared minus negative 2x squared is 4x squared. Bring down the negative 3x. And then I'll need a 4x up here. So 4x squared minus 8x. Okay, we'll subtract that out. Those cancel. Negative 3x minus a negative. Well, minus a negative becomes positive, correct? So we're going to get 5x minus 10. Put a plus 5 up top. And that gives us 5x minus 10, which gives us a remainder of 0. Right, so we see it does work. It also tells us here that this factorization that we were hoping that we knew existed is going to be x squared plus 4x plus 5. Right, so that's where we're going to do a lot with synthetic division, or I'm sorry, with long division and then later with synthetic division, is we can look to see if we have a factor, and then once we get it, it's worth the trouble to go ahead and find out what the quotient would be. Again, because we don't need to put a plus r of x, because the remainder is 0.